In this tutorial, we will talk about industrial instrumentation flowmeters part 5. The topics of discussion are thermal flowmeter and the different types of thermal flowmeter, which are rate of heat loss flowmeter, temperaturized flowmeter, and one example hot wire anemometer. The next type of flowmeter is the thermal mass flowmeter. They are also called dispersion or immersible mass flowmeters. They comprise a family of instruments for the measurement of the total mass flow rate of a fluid, which is primarily gases, flowing through closed conduits. The rate of heat absorbed by a fluid flowing in a pipe or duct is directly proportional to its mass flow. That is the underlying principle of the thermal mass flowmeters. Thermal flowmeters measure mass flow rate by means of measuring the heat conducted from a heated surface to the flowing fluid. Relying on the principle that a fluid flowing past a heated temperature sensor removes a known quantity of heat as it passes, thermal flowmeters measure either how much electrical power is required to maintain the temperature of the heated sensor or the temperature difference between the heated sensors and the flow stream. Either of those values is directly proportional to the mass flow rate. Thermal flowmeters are used almost entirely for all gas applications. Their design and construction make them popular for a number of reasons. They feature no moving parts, have nearly unobstructed flow path, require no temperature or pressure correction, and retain accuracy over a wide range of flow rates. Straight pipe runs can be reduced by using dual plate flow conditioning elements, and installation is very simple with minimal pipe intrusions. Thermal mass flowmeters are gas flowmeters based on the relationship between convection, heat transfer, and mass flow. There are two types of thermal flowmeters. Those are rate of heat loss flowmeter and temperaturized flowmeter. The first type of thermal flowmeter is the hot wire flowmeter. Here, the rate of heat loss of the thermal flowmeter is measured and the heat losses are picked up by the temperature sensors like thermistors, thermocouples and others. The governing equation is Qt equal to del T into K plus 2 under root small k Cv rho pi d V average, where Qt is the rate of heat loss per unit time, del T is the mean temperature elevation of wire, small d is the wire diameter, K is the thermal conductivity of fluid stream, and rho is the density of the fluid stream. Cv is the specific heat of the fluid stream and V average is the average velocity of the fluid stream. In this equation, V average, Qt and del T are all unknowns because they change with time while the other variables are known. However, Qt and T can be obtained through measuring devices, thus we can solve for V average from this equation. Here we see the pictorial representation of the hot wire flowmeter. We see that in both the upstream and at the downstream we have two temperature sensors to pick up the heat loss. The second type of thermal flowmeter is the heat transfer flowmeter. The temperature rise thermal flowmeter measures the temperature changes of the flow as it passes through a heat source. Numerically, W equal to H by del T Cp, where W is the mass flow, H is the heat input, del T is the temperature change, and Cp is the specific heat. W and del T are unknown in this equation. Del T can be measured, thus W can be calculated. Thermal flowmeters are gas flowmeters only and can be used as liquid switches but not as liquid flowmeters. Due to the sudden drop in del T because of the higher cooling rate of liquids compared to gases. The higher cooling rate of liquids prevents the transmitter from calculating an adequate flow range in liquids. Here we see the pictorial representation of the heat transfer flowmeter. We see T1 and T2 as the two thermocouples which act as the temperature sensors. The hot wire anemometer is the most well-known thermal anemometer and measures a fluid velocity by noting the heat convection away by the fluid. The core of the anemometer is an exposed hot wire, either heated up by a constant current or maintained at a constant temperature. Both these possibilities are shown in the figure here. In either case, the heat lost to fluid convection is a function of the fluid velocity. By measuring the change in wire temperature under constant current or the current required to maintain a constant wire temperature, the heat loss can be obtained. The heat lost can also be converted into a fluid velocity in accordance to convective theory. Typically, the anemometer wire is made up of nickel, platinum or tungsten and is about 4 to 10 micrometer in diameter and 1 millimeter in length. For commercially available hot wire anemometers, they have a flat frequency response less than 3 dB up to 17 kHz for average velocity of 9.1 meter per second, 30 kHz for 30.5 meter per second and 50 kHz for 91 meter per second. Due to the tiny size of the wire, it is fragile and thus suitable only for clean gas flow. In liquid flow or rugged gas flow, a platinum hot wire coated on a 25 to 150 mm diameter quartz fiber or hollow glass tube can also be used instead. The governing equation for the hot wire anemometer is the King's law, which numerically is given as hd by k equal to 0.3 plus 0.5 into under root rho v d by mu. This factor rho v d by mu is nothing but Reynolds number. This heat transfer phenomenon has a problem. When a heated element is positioned very close to a solid surface, a sudden increase in heat flow transfer occurs. In order to compensate for this sudden increase, King derived a solution from an infinite cylinder in an incompressible low Reynolds number flow in 1914. The heat transfer coefficient H is a function of the fluid velocity V as shown in the equation above. The advantages of the thermal flow meter are direct measurement, handling of high temperature and pressure fluctuation, very high accuracy, that is plus minus 1% of full scale, and very high repeatability, good response for very low flow rates in gases, excellent rangeability and excellent turn down ratio of typically 50:1, and these flow meters, they do not have any moving parts. The limitations that these flow meters have are they can only cater to clean and non-abrasive fluids. The presence of moisture in the fluid can lead to much inaccuracies and the initial cost is pretty significant. Students can refer to the following links and references for additional reading. Thank you.